Alright, y'all, this is going to be a short little video on circuit notation. I just want to kind of lay the groundwork so that in the upcoming lectures, it'll be hopefully clear what I'm talking about. So, let's hop into it. Okay, circuit notation. We're going to talk about a few different items, a few different circuit elements, and how we write them down. So, the first thing to talk about is batteries or voltage sources. So, the way that a voltage source is written in a circuit, first of all, let's just talk lines. So a line in a circuit is just a wire. It has zero resistance. It just carries charge flawlessly. So this is an ideal wire. True wires always have some resistance. But when we talk about wires in physics, we will typically assume resistancelessness. There we go. No resistance. Okay, so we write a battery like this. So a battery has a lead, a wire that comes into it. Then it has a negative terminal and a positive terminal. So by default, you should assume that the longer line, like this one over here, this is the positive terminal, this is the negative terminal. However, if you want, like no one's going to fault you for going in and writing in a little plus and a little minus. So what a battery like this usually tells me is that it's, again, it's supplying energy to the circuit. It's analogous to a pump. So it's analogous to a pump from the fluid side of things. Okay, there's a few ways that we denote batteries. So the way that I would write in a battery voltage is this kind of capital E looking thing, squiggly E. That means battery voltage, or current, or how do I say this? Voltage source voltage. Okay, so this thing has units of volts, capital E. The next thing to talk about is a resistor. So say I had some resistive element, some load that I want my circuit to deliver energy to. So I denote a resistor, R. I denote a resistor with first a little input wire, then a resistor itself, which is suggested to be kind of a jagged thing, right? So it's kind of like rough walls in the pipe. It's this jagged thing, and then an output lead. So usually what one does when marking a resistor's resistance, if you know a number for it, you just kind of pick a point directly above or below and say 2 ohms, for example. So I mark it in units of ohms. Similarly for this battery, I could say plus 3 volts if I knew the voltage. Okay. Next thing, currents. So let's say that I hooked this battery up to this resistor with a wire. Well, as a result, some net positive charge is going to be free to flow from the positive side of this battery to the negative side of this battery. So it's allowed to go around the circuit now. I've closed my circuit. So when I've closed my circuit, a current will begin to flow, and I can mark that current with an arrow, usually just adjacent to the circuit like this, an arrow, and mark it as I. So if you have branches in your circuit, like if you have, a point where current can go multiple directions, say, something like this, if I had more stuff down the line over here, that then connected back. Okay, so if I have a branch, I can have multiple different currents. So usually what we do to talk about multiple different currents is introduce subscripts. So I'll call this one I1. And if I know its value, I might mark that in as like, I don't know, let's call it, what would it be? 1.5 amps, something like that. We'll discuss how I got that number here in a bit. Okay. Last thing to talk about is measurement devices. So there are a few measurement devices that you might see when you're playing around with simulations or when you're looking at DL, things like this. So the first one is an ammeter. So an ammeter measures current. Kind of suggestively, it measures amps. So yeah, all right. So an ammeter is typically denoted by a circle with an A on it. I've occasionally seen a circle with an I on it for current, but yeah, usually it'll be a circle with an A. And an ammeter is placed somewhere on top of a circuit, usually on a wire, ammeter, and it'll read out for you the current at that point. What you're really doing, so this is an aside, this is not on the test, but what you really do in practice with an ammeter is you hook it up, you like hook up a wire from some part of your circuit to a negative lead on your ammeter. Yeah, and then you hook up a positive side to some other wire, so it interrupts your circuit. Current has to flow through the ammeter. By contrast, a voltmeter, which measures voltage, voltmeter, which measures voltage, wow, okay, handwriting, is usually denoted by a V with a little circle around it. And when a voltmeter measures voltage, I should probably be more explicit and say it measures a change in voltage. It measures a difference in voltage between 2 points. So for example, I might connect a voltmeter across this resistor or over this resistor. Usually you say across though. So I measure the voltage across this resistor by hooking up my voltmeter on opposite sides of it. So I would see a voltage drop, I would see a change in voltage, a delta V, associated with the difference in voltage between these 2 points, points 1 and point 2. Comparable to in fluids, how we would apply the Bernoulli equation between 2 points. So this is analogous to a pressure difference between 2 points. Okay, so if I were interested in finding that voltage difference, I could measure it. I would see that in this case, the voltage at the second point minus the voltage at the first point would actually be negative 3 volts. I'd see a voltage drop of 3 volts across this resistor. And again, I'll explain how we get those numbers in a future lecture, or a future part of this series. Okay, so that's it for notation. One thing to notice, actually, I'll give you one more little small caveat here. Again, this is not something that I expect to test you on, but just in case this is like confusing, a voltmeter, an ideal voltmeter, does not carry any current. So an ideal voltmeter has high enough resistance that current doesn't want to flow down this little pink section here. So an ideal voltmeter doesn't really interfere with the circuit. No current. All right, that's it for this one. We'll see you in the next one when we talk about Kirchhoff's laws.